Hello and welcome to the AI Research Roundup. I'm your host Alex, and today we're looking at some interesting developments in AI. We'll be discussing a paper titled ChatTS, Aligning Time Series with LLMs via Synthetic Data for Enhanced Understanding and Reasoning. This paper tackles how large language models can better understand and reason about time series data, things like sensor readings or financial data over time. The researchers introduced a new model called ChatTS. A really key part of their approach is using synthetic data, basically artificially generated examples, to train the model, which helps overcome the common problem of not having enough real-world training data for this kind of task. Okay, so Figure 1 here gives a really good visual of what this looks like in action. You can see on the right, there are several time series plots, things like HTTP requests, success rate, disk I/O, typical system metrics. And on the left, you have a user asking questions about this data, and the LLM providing answers. For instance, the user asks about fluctuations in the success rate, and the LLM correctly identifies downward spikes. Then it even correlates issues across different metrics, like disk I/O and CPU usage, around the same time point to suggest a possible system overload. It shows how the model can understand and reason about these complex patterns. Building on that example, Figure 2 actually compares a few different ways LLMs might tackle this. Besides the ChatTS approach, which directly processes the time series data arrays like we see on the bottom right, other methods exist. You could try converting the time series values into a long text description, or use an agent-based approach that breaks the problem down step by step, or even feed an image of the plots to a vision model. This figure really lays out the landscape of how people are trying to get LLMs to understand these time series patterns. Okay, so Figure 3 here actually shows us how they generate that synthetic data for training ChatTS, which I mentioned earlier. It starts with selecting specific time series features or attributes, like trend or seasonality, from a pool. Then, based on these selected attributes, the system generates two things: the actual time series data, the wavy line plots, and descriptive text about it, including Q&A pairs, using a method called time series eval instruct. This generated time series and its matching text are then used together to train the model. Going further, Figure 5 actually digs a bit deeper into that time series eval instruct method we just talked about for generating the Q&A pairs. You see it starts with a simple seed Q&A about a basic trend. Then, using different evolution types like breadth, depth, reasoning, or situation, shown at the top, it transforms that simple question into more complex ones. It pulls in more attributes from those pools we saw before, like period or local fluctuations, and even correlations, to create richer questions that require more reasoning, like comparing multiple metrics or asking about specific situations. Okay, so Figure 4 actually zooms in on the start of that synthetic data generation process we saw outlined in Figure 3, specifically how they create the time series data itself before generating the questions about it like we saw in Figure 5. It shows starting with a big set of all possible attributes: trend, periodicity, local fluctuation, noise. Then, for a specific metric like request count, an LLM selects a relevant subset of these attributes. An attribute sampler then assigns concrete values, like the period of the sine wave or the amplitude of a spike. And finally, a generator combines these components to create the actual time series graph. So we've seen how the synthetic time series data gets created. Figure 7 now shows a crucial step in how the model actually handles this data when it's fed in. It's called value-preserved normalization. You see the original numbers for something like HTTP requests, like 105.1, get converted into a normalized vector, here shown as 1.0, 0.98, and so on. But importantly, the model also gets told the original scale information as part of the text prompt. See the value scaling and value offset? This means it still knows the real magnitude of the data, not just the normalized pattern. Alright, so building on that normalization step we just saw, Figure 6 actually gives us a look at the overall model structure for ChatTS. you can see it takes in both the time series data, like those HTTP requests and success rate lines, and the text input, like the user's question. The time series get broken down into these smaller chunks or patches, while the text gets tokenized as usual. Then there are separate encoders, one specifically for the time series patches, and another standard one for the text embeddings. And here's a really neat part. The encoded time series features are actually inserted in between the corresponding text tokens before everything goes into the main LLM. This helps keep the context of which data belongs to which part of the text. So yeah, that's the ChatTS architecture, interleaving those time series patches with the text. Overall, this paper really shows how synthetic data can effectively train LLMs on tricky time series tasks. And that value-preserved normalization helps it grasp the real-world scale, not just abstract patterns. It's a big step towards AI that can understand and reason about more than just language, bridging that gap to numerical data. Well, that's all for this episode of the AI Research Roundup. Thanks for tuning in. I'm your host, Alex.